Hello everyone, let us solve this problem based on conductors which has came in IIT 2009 problem it is. Okay, so as we are seeing that we are given with a three concentric metallic spherical cells, okay, of radii r, 2r and 3r, and we can see here that the charges which are given here is q1, q2 and q3. And what the condition which is given to this problem is that if the surface charge density means outer surface charge density are equal, then we have to find the ratio of these charges q1 is to q2 is to q3. Okay, and we have four options, and let us see how we can solve this problem. Okay, so first of all, when you get this type of problem, we have to understand one thing. Directly don't rush into the problem. First you have to understand what will happen if this thing is if the charges are given to a conductors. So the basic concept is that whenever we are getting a charge to the conductor, the charge will come to the surface. First of all, this is the thing. Okay, so here no charge will be residing inside. In the first I am talking about the first cell of radii r. So all the charges will come to the surface. Okay, no charges will be inside. So complete charge q1 will come to the surface. And as we know, fundamentally we know one thing, that no electric flux means electric field lines cannot cross or penetrate any metallic surface. Okay, so if this q1 charge positive, if this q1 charge is positive and if positive charge is distributed like this, what will happen here? The flux will be generated, and total flux has to be terminated here in the innermost side of the second cell. So minus charge will be induced here. Okay, so exactly minus q1 charge will be induced in the innermost surface. And since this is the induced charge minus q1 here, okay, inside minus q1 charge will be induced. So this will come from the outside. So outside the charge will go to plus q1. So again here the charge will be plus q1, and outside we know that plus q2 was before it was given. So it will be q1 plus q2. Finally the charge outside will be q1 plus q2. And again the same, applying the same concept, that q1 plus q2 charge will just generate the electric field lines, thereby generating electric flux, and all the electric flux has to be terminated at the innermost surface of the third one. Otherwise the law will be violated, that we know that no flux has to penetrate through any metallic surface. So again we can see that minus, here the induction will be minus times q1 plus q2 charge will be induced here. And from where it will come? It will come from outside. So outside charge will be q1 plus q2, and previously we know that it has q3 charge given previously. So in this way, first of all we have to understand the things, how the charge induction is there, and after that the things are very simple. Okay, we can just apply the conditions which is given in the question, that is the outer surface charge density is equal. So we can find sigma 1, sigma 2, sigma 3 and we can calculate very easily. So what we are getting about sigma 1, let us calculate. What is surface charge density? Charge upon surface area. And surface area of any sphere we know that it is 4 pi r square if r is the radius. So first of all, what will be for the first sphere, what we are getting? Surface charge density will be simply q1 by 4 pi r square. Very simple. Okay, 4 pi r square. What will be sigma 2? Sigma 2 will be simply what will be the final charge on the outer sphere of the second one? It is not q2. Okay, after induction the charge is q1 plus q2. So here the final charge is q1 plus q2 divided by 4 pi, and what is the radius? 2r whole square. 2r whole square. Okay. And third one, what is the sigma 3? Okay. Surface charge density on the third cell, that is the outermost cell. What we are getting there? Now the final charge on cell is q1 plus q2 plus q3. So the final charge is q1 plus q2 plus q3. And what will be the surface area? The radius we know that it is 3r. So it will be simply 4 pi into 3r square. Okay. Understand it? This is clear. And now the things are very simple. All this sigma 1, sigma 2, sigma 3 all are equal, and we have to find the ratio. And let us proceed on the next page. Okay. How we can calculate? It's very simple to understand. Okay. Let's see. We have got sigma 1, sigma 2, sigma 3, and I am writing it. Sigma 1 is simply q1 by 4 pi r square. Very simple. Is equal to sigma 2. What is sigma 2? It is q1 plus q2 divided by 4 pi 2r whole square. Okay. It will become 16 pi r square. Okay. That is also equal to the third one, that is q1 plus q2 plus q3 divided by 4 pi, and what is the radius? That is 3r square. And let us this is same, so let us consider it to be some quantity, that is x, for example. Okay. Understanding? And now we can calculate it very easily. Let's see how. What will be q1? From here, if we equate this and this, and secondly we will equate this and this, and third we will equate this and this. This is the mathematics which we will follow. So what we are getting, first we will equate this first and last. So we will get q1 as x into 4 pi r square. Very simple. Okay. Clear? And if you equate this and second one with last, what we are getting? We are getting as q1 plus q2, q1 plus q2 will be equal to x into this will be 4 pi 2r square, means it will be 4r square. Okay. So this will be the thing. This is the second equation. So let us consider this quantity to be some other quantity. Let it be c. Okay. So what will be this one? Okay. If this is c, this will be 16 pi r square. Okay. This will be 16 pi r square into x. Okay. 16. Okay. 4 into 4. That is, we can write here in this way. 4 into, let us do this way. It is simply, okay, just 1 minute. So here we can write here as x into 4 pi into 4r square. So this we can write as, if this quantity is c, we can write this one as 4c. Okay. And q1 is c. So q2 we can get from here as 3c. Okay, c will go this side, so it will be 3c. Similarly, if you equate this third one with last, what we are getting is, if you do it, what we will get is, let's see, we will get as q1 plus q2 plus q3 is equal to 4 pi r square. 3r whole square. Okay. 3r whole square into c. Into x. Okay. I am equating, just I am, this portion I have taken from downside. Okay. I have just cross multiplied it. Okay. Now you see q1 plus q2 plus q3 is equal to, and we know very well that 4 pi r square x we are taking as c. So it will be simply 9c. Okay, and we know that q1 is c and q2 we have got 3c. Okay, so simply q3 will be 5c. And once we see the ratio q1 is to q2 is to q3, what we are getting? It is simply 1 is to 3 is to 5. Okay, so this we are getting as answer 1 is to 3 is to 5. Okay, 1 is to 3 is to 5. Let me discuss here one point here which is very important. Okay, let us see that. You see here, once I have solved this problem by using by induction, if anybody who is just not aware of this induction, if he solves it straightforward, okay, what he will get the answer. If sigma 1 is the surface charge density, he will directly write q1 by 4 pi r square. Sigma 2 he will directly write as q2 by 4 pi into 2r whole square. Sigma 3 he will directly write as q3 by 4 pi into 3r whole square. And that option 1 is to 4 is to 9 is also present in the multiple choice question. Okay, so be very careful while solving the problems. So this is the catch which we have to understand, that first of all we have to analyze the problem, and after analyzing that we have to solve the problem. Okay, let us move to the next problem. Let us see this second problem, which is saying that a solid conducting sphere having a charge q is surrounded by an uncharged concentric conducting hollow spherical cell. As you can see in this question, that we have a solid spherical cell by yellow color here, and a red color which I have shown here, that is the hollow conducting sphere. Okay, hollow cell, we can say hollow spherical cell. So what this question is asking is, let the potential difference between the surface, means this is the surface of the solid one. Okay, I can denote by another one so that we can see it. Okay, let us see the surface here, surface of the solid sphere. Okay, let we can denote it by A, and the surface of the hollow sphere we can denote it by B. So what the question is asking is that let the potential difference between the surface of the solid sphere, okay, and that of the outer surface of the hollow cell be V. Okay, so if the potential difference between A surface of the inner surface of the solid sphere, which we have denoted as A, and outer it is B, so potential difference is B, V. Okay, potential difference is V. Let us write it. Okay, so we have to find in a condition, okay, that if outer surface has been given a charge minus 3q, okay, then we have to find the new potential difference between the same two surfaces. Okay, that is the inner surface and the outer surface. And we can see, okay, let us proceed with the first case. In first case, what is there? We have given that this inner surface and outer surface potential difference is V. So we have to find the potential difference at this point A and B, and we have to find the differences, and we have to call that difference as V. Let us see. So in case 1, what we have? In case 1, simply the inner surface, there will be no charge in the inner body of the conducting sphere, as we all know. That is the basic concept, that all the surface means all the charges, no charge will reside inside, all the charges will come to the surface of the sphere. Okay, to maintain the minimum potential, or you can say it is the stability concept, we can understand that. Okay, so in case 1, what will be the potential at surface A? Very simple. Okay, as we know, that is kq by radius is r1. Very simple. What will be the potential at the surface B? What will be that at B point? As we know that whatever charges here inside it is, we have to consider that all the charges are concentrated at the this point at the center. We can call it this center as O. Okay, so what will be the potential at B? It will be simply kq by r2. Okay, this is the basic concept. Okay, that is why I am not explaining too much. kq by r2. And once we find the difference, what we are getting? VA minus VB. What we are getting? That is simply kq will be common. So kq 1 by r1 minus 1 by r2, and we call it V, as which is given in the problem. Now next, what we have to do? In second case, minus 3q charge is given to this outer surface, and then we have to calculate the potential at A and B again, and then subtract it and see what is happening. Let us do on another page. So what is the case? If minus 3q charge is given to the outer surface, the potential at inner surface will be, due to the inner surface charge, what will be? Let us draw that figure to make it clear. If this is the thing, this is the inner solid sphere. This is given a charge q, outer surface it is minus 3q. So let us see what is happening. So what will be there? Inner surface, due to this q charge, what will be the potential at this surface A? That will be simply kq by r1. kq by r1. And due to this outer surface, due to this outer charge, what will be the potential at A? The potential at each and every point inside will be equal. Okay, and that will be minus 3 kq by r2, because the charge is minus 3q, and due to negative charge the potential is negative, and due to positive charge the potential is positive. So simply this is the potential at A. What will be the potential at B point? Means this point, outer surface, B point. Due to charge q, it will be simply kq by r2. Okay, and this by this minus 3q, we have minus 3kq by r2. So what we are getting? Minus 2kq by r2. And once we subtract it, VA minus VB, what we are getting is, you can see, we are getting as kq by r1 minus 3kq by r2 minus, again minus, so it will come plus 2kq by r2. So what we are getting as, simply, okay, this will be minus kq by r2. So again we are getting the similar thing, kq 1 by r1 minus 1 by r2, which is also equal to V. Okay, so very interesting thing has came here, that once the charge which is given to the outer surface, that is minus 3q charge is given to the outer surface, there is no change in the potential difference between this surface A and B. Okay, so we have to note one thing, that the potential difference depends on the charge on the inner sphere only. Okay, so we have to always be clear with this concept, that whatever will be the change in the potential difference, that will be due to the inner sphere only. That will not be due to the outer sphere. Whatever charge you give to the outer cell, it will not affect the this potential differences between this surface A and B. This is one concept which we have to keep in our mind. Let us solve this another problem. what this problem is, that we have two isolated metallic solid spheres of radius r and 2r. Okay, and they have kept so far. Okay, the spheres are located far away from each other, and they are connected by a thin conducting wire. So I can show that wire also here. They are connected by a conducting wire. Okay, so we have to find the new charge density on the bigger sphere. To make it very clear, this what this question is asking is, we have two isolated metallic solid spheres of radii r and 2r and are charged separately. Okay, before this connection which I have shown here, are charged, this both the spheres are charged in such a way that this both have the same charge density, and it is given in the problem as sigma. Okay, and now they are connected, and we have to find the new charge density on the bigger sphere. On this bigger sphere we have to find the new charge density. So it's a very simple thing to, we have to move in a very straightforward manner. It's a very simple problem. Okay, this is also a IIT problem which has came in the year 1996. So let us find if the both have previously, means in the previous case, let the before connection the charge on this one is q1 and the charge on this one is q2. So we can find q1 and q2. How? The surface charge densities are same. So in terms of surface charge density, we can find q1 and q2. What will be q1? Very easily we can find out q1 as, we will get it as 4 pi r square is the surface area into sigma. Very simple. What is this means, what is this? Surface area is 4 pi r square of this sphere into sigma is q1. What is q2? Surface area of this sphere will be simply 4 pi into 2r whole square into sigma. Okay, so this will be simply 16 pi r square sigma. Okay, clear? Understandable? Now once this connection has, this all the things which I am doing here, it is before connection. Try to understand, this is before connection. Okay, before connection, keep it in mind this one. After connection, what happened? Let this charge q1 has become q1 dash, and this charge q2 has become q2 dash. Why this is happening? Try to understand that. Always the charge will flow from high potential to low potential, and the flow will stop until the flow will be there, unless and until the both the sphere will come to the same potential. Understanding? So the charge flow will be always there from high potential to low potential, and the charge will stop when the potentials are equal. Okay, now you see, so by conservation of charge, what we can find here is that q1 plus q2, I am applying the conservation of charge, that is q1 plus q2 is the sum of the charges, will be also equal final also. After connection also the charge will not be created, or nor it can be destroyed. It is the law of conservation of charge. Okay, so it will be q1 plus q1 dash plus q2 dash, and we are getting as, once we just add this one and this one, we are getting as 20 pi r square sigma. Okay, 20 pi r square sigma. Let us consider, let us call this equation as 1. Okay, and let us move to the next page to solve this problem. Okay, so as I have discussed previously, that the charge transfer stops when the potentials on a sphere of two spheres are equal. Okay, so let us calculate that thing, that what will be the final potential, okay, of this first sphere and second sphere, and let us equate it. Okay, so what we are getting is q1 dash by 4 pi epsilon naught. I am applying the formula of potential kq by r simply. So it will be for first sphere, it is final charge is q1, so it will be simply final charge is q1 dash, so it will be k is 1 by 4 pi epsilon naught q1 dash by r. And this is also equal to, okay, this is the condition when the charge flow has stopped and final charges are q1 dash and q2 dash. This will be also equal to q2 dash divided by 4 pi epsilon naught into 2r. Okay, so this 4 pi epsilon naught will cancel, and from here we will get as q2 dash is equal to 2q1 dash. Okay, this we call as equation second. And from equation first, what we have got, let us see. First equation we have got as q1 dash plus q2 dash is equal to 20 pi r square sigma. Okay, as in the previous slide we have got this one. Okay, 16 pi r square sigma and 4 pi r square sigma. Okay, so that is correct. So this is the thing. Okay, so this is was equation first. From first and second equation we can calculate and get q1 dash. So let us put q2 dash here. We will get 3q1 dash will be equal to 20 pi r square sigma. Okay, so q1 dash will be simply equal to 20 by 3 pi r square sigma, and similarly q2 will be double of that. Okay, because double of that, so it will be 40 by 3 pi r square sigma. Okay, let us come to the next slide. Okay, here what we are getting, we have to calculate the final charge density. So charge density sigma 1 dash on the first sphere, q1 dash is the charge upon area, surface area, so it will be 4 pi r square, and we have got q1 dash. Okay, so that is 20 by 3 pi r square sigma divided by surface area, that is 4 pi r square, and this 4 pi r square pi r square will cancel. This is 4 5 ja, so it will be 5 by 3 sigma, 5 by 3 sigma, understanding. And what will be sigma 2 dash? It will be very simply q2 dash divided by 4 pi, okay, into 2r whole square. So what we are getting is 40 by 3. Okay, it will be 40 by 3 pi r, that I am writing about q2 dash. Okay, so 40 by 3 pi r square sigma divided by 16 pi r square. So pi r square will cancel, and this will be simply this will be 8 2 ja 8 5 ja, so we are getting 5 by 6 sigma. Okay, so these are the final charge density, okay, on the two spheres. It's a very straightforward problem. We have to apply the conservation of charge, and after that we have to apply what the question is saying, that surface charge density is same. We can do it very simply. Okay, one another interesting problem, this is also from IIT 1990 problem. It is very simple. It is actually once we are clear with our concepts, you can see it's a very simple problem. So what this question is saying, let me explain the question very in detail, and then we can solve it very easily. We have 3 spheres, concentric spheres, having the same center, that is called concentric. So we have 3 concentric spherical metallic cells, and we can name them A, B and C. Okay, in such a way that we have the radius A, B and C. Inner radius is A and outer radius is C. Okay, and we have also given that the surface charge density, inside it is sigma, middle one it is minus sigma, surface charge density, and outside it is plus sigma, okay, respectively. So first question they are asking is, we have to find the potential of the three cells, okay, that is of A, B and C. Understanding? So this is a very straightforward application. Once we are clear with our concept, as I have told you earlier also, it's a very simple thing. So first of all, knowing the surface charge density, let us find the charges on the three spheres. Okay. So we can write on the first A cell, what is the charge? Simply surface area is, if radius is A, surface area is 4 pi A square into sigma. 4 pi A square into sigma. Charge on B, this is also simple. The charge will be negative because surface charge density is minus sigma. So it will be minus 4 pi B square. 4 pi B square is the surface area into sigma minus sigma. Okay. And what is QC? QC is simply surface area is 4 pi C square. 4 pi C square into sigma. Okay. This is QC. So once we know the charges on the three sphere, now we are in a position to find the potential potential at the point A, B and C. Okay. So first we will write for A and let us see what we are getting. So potential at A will be simply equal to, at the surface point A, we will get as KQA by A. KQ by R, radius is A. And for this one, this minus sigma, for this QB charge, what will be the potential at A? We know that inside every point the potential will be same. What is the potential at the surface? That potential will be, once we move inside, every point interior will be always same, because interior point of the interior point of the spherical cells, or we can say of the conducting metallic cells, or of the spherical metallic cells, are always equal, because inside always electric field will be 0, as I have discussed earlier. Okay, that inside there is no electric field, so potential inside at each and every point inside will be always equal. So what is the potential at the surface? Every point inside will be at the same potential. So by that concept we can write here as, since the charge is negative, so minus K QB. What is the potential here at B, surface B? That is KQB by B. At every point inside the potential will be same. Plus, due to this one, same concept as I have discussed for this one, same concept I can write for C also. That is KQC by C. Okay, and I can put the value of QA, QB, QC in this, and let us see what we are getting. Okay, let us see what we are getting. We will get VA is equal to, once we put it down, the calculation part which we do, K is simply 1 by 4 pi epsilon naught. So we will get here as sigma by epsilon naught A minus B plus C, as I have taken sigma by epsilon naught common from this one. Okay, same thing we can write for B1, potential at B. Now I am writing faster to make, as we have cleared the concept, same concept will be there. For B, okay, it will be, let me draw it here to make it understand. Okay, understandable. This one A, B and C. Okay, so this is A, B and C radius. Okay, so inside it will be at this surface point B. This is the point B. If you are writing the potential, due to inner one, it will be simply K QA by B, and due to this one at B point, it will be simply minus KQB by B, and due to outer surface, by similar concept, it will be simply plus k qc by c. Okay, so once we take again common, sigma by epsilon naught a square by b minus b. Okay, because previously you can see that a portion was cutting, but here it is not cutting. Okay, so that is why a square is coming here, minus b plus c, and in this b, 1b and 1c are cancelling. Okay, that is why here one denominator b is coming here. Okay, and a square term is coming upside, and 1b is cutting here, and 1b c is also cutting here. Okay, so we have written vb. Now let us write for c. Okay, let me come to the next page and write for c, potential at c, and potential at c will be kqa by c minus kqb by c plus kqc by c. Okay, and okay, we are getting as a square sigma by c epsilon naught minus b square sigma by c epsilon naught. This are just algebraic thing. We can do it very simply. Once we write this equation, no, other things are very simple. Just algebraic calculation. Plus c, school level calculation, plus c epsilon sigma by epsilon naught. So once we take sigma by epsilon naught common, and what we are getting, let's see, this is a, not q, this is a, so we can easily see this. So sigma by epsilon naught into a square by c minus b square by c plus c. Okay, this is the potential at c. Okay, so these are also very simple thing. Okay, by knowing the concept, we can write it very simply. In this question only, another question has been asked. Okay, b point, and that is if we have the three cells again, if I am drawing that. Okay, so if the cells a and c, means this cell a and c, if this point is c and this point is a, if the potential of these two are same, means potential of a cell and c cell are equal. So very simple, we have calculated the potential at a and c, and we can equate it and get the result. We have to find the relation in radii. Okay, in the we have to get the relation in radii a, b and c. Let us see. We know the relation, we have got va. Okay, that is sigma by epsilon naught a minus b plus c, and that is equal to sigma by epsilon naught a square by c minus b square by c plus c. So sigma by epsilon naught cancels. Okay, and one c will also be cancelling, and a square minus b square by c. So we, and this is a minus b, so a minus b is equal to a plus b into a minus b. We can write it. What I am doing is a square minus b square, I have taken LCM, and square term I have opened like this and cancels this one, and we will get a very simple relation as, we can multiply this one this side, we are getting as a plus b is equal to c. So this is the relation which we are getting in radii. So this is a very straightforward thing. Okay, let us solve one last problem from this is also from IIT 1981. A charge q is distributed over two concentric hollow sphere of radius r and capital R. Okay, such that the surface charge densities are equal. The question is very simple, and that is, the surface charge densities are equal and the charges are distributed in such a way that surface charge densities are equal. And what we have to find? We have to find the potential at the common center O. Okay, this is the common center O. We have to find the potential at the common center O. So we have to distribute this charge Q. Okay, Q charge is distributed. So let inner surface has got Q. So the remaining outside it will get as Q minus Q. Okay, because total charge is Q. So apply the first thing, that the surface charge densities of inner and outer are same. So by applying that, we will get as Q by 4 pi r square is equal to, this is the surface charge density of inner, charge upon surface area, and outside outer surface has charge Q minus Q, so it will be simply Q minus Q by 4 pi r square. Okay, 4 pi r square. Clear? So 4 pi cancels, and once we divide this Q downside, okay, this Q, if I divide it downside, what we are getting is Q by Q minus 1 is equal to r square by r square. Okay, just be careful here, calculation. So Q by Q we are getting as 1 plus r square by r square. Okay, so from here, if I okay, just multiply this one and take this one downside, what we are getting as Q is equal to, what I will get is Q is equal to Q by 1 plus r square by r square by r square. Okay, I'm getting this one. So let us move on next page. So Q will be simply equal to Q by 1 plus r square by r square. So that will be equal to r square, take upside, so it will be qr square by r square plus r square. Okay, similarly we can find out Q minus Q. Okay, just to find out Q minus Q, so what we will get, Q minus QR. Why I am finding this? Because I have to find the potential, so I need this charge Q minus Q, which is outside charge. So Q minus Q r square divided by r square plus r square. Okay, that is equal to QR square plus QR square minus QR square divided by r square plus r square. Okay, so what we are getting is, this will be cancelled, so we are getting simply as QR square by r square plus r square. Just keep these two things in our mind. Q minus Q is this one and Q is this one, and let us apply the simple formula which we know. Okay, let me draw that figure to make the things clear. This is inside sphere, this is outside sphere. Okay, circle is not perfect, so this is okay. So inside radius is r, outside radius is capital R. This is the common center O. Inside charge is Q and outside charge is Q minus Q, as we have calculated it. Okay, so the potential at point O will be, for this one it will be K, we can write it here, 1 by 4 pi epsilon naught, we can write K also, no problem, Q by R. Let me write K so it will be clear, no need to write this much. Okay, K, just 1 minute, K Q by R plus outside we can see here it will be K q minus q, this is the charge, by capital R. Okay, putting this value previously, q and q minus q, what we are getting is v naught is equal to kqr square divided by r into r square plus r square, okay, plus kqr square by r square plus r square. Okay, one r cancels and one this r also cancels. So what we are getting is v naught is equal to kq by, we can take common this one, kq by r square plus r square into r plus r. Okay, r plus r, kq by this one r square plus r square I have taken common, and what I am getting is this one. Okay, so this is the last problem, and you can see very means fundamentally, once your fundamentals are clear, these questions are means damned easy. Okay, so fundamentally once you are very much clear with your concepts, then the questions is just algebraic calculation, school level, 8th level, 7th level calculation. Thank you.